Hey coders, what's going on guys? Super excited for today's tutorial. So we're actually going to be looking at two problems today. So the first one we're going to be looking is balance a binary search tree, and the second one will be convert sorted array to a binary search tree. So I'll say like it's quite important to kind of like start with easy problems when you're starting out. Then as you go along, then you transition to medium and hard question. And the goal today is just to show you how kind of like easy some of these medium problems are if you understand the easy problems, and as much as you transition to hard problems also. That's the goal essentially, like just to show you how it kind of like how important it is for you to kind of like solve easy problems. And if like they're gonna give you the confidence, then after you get in the confidence, then you move to medium problems, then you move to hard problems, right? So cool. So let's start with the easy problems, right? So they say that convert a sorted array to binary search tree, right? So given an integer array nums where the elements are sorted in ascending order, so the elements are sorted in like increasing order, like from 0, 1, 2, 3, 4 up to infinity, convert it to a height balanced binary search tree, right? So like I covered this in the previous video, I think, whereby I actually explained how we can actually validate a height balanced binary search tree, right? So just have a look at it if you don't understand what a height balanced binary tree is. So essentially a height balanced binary tree is a binary tree in which the depth of two subtree of every node never differs by more than one. Okay, so like I said, I've explained this and we solved the problem. So check it out if you don't understand what a height balanced binary search tree is, right? So what is it that they want us from us? So let's go to Whiteboard and try to understand how we're going to actually solve this and what is it that they want from us. Okay, welcome to Whiteboard, right? So what we want to do now is that we actually want to kind of like solve the problem, right? But what I usually do is to follow a systematic approach, right? Like my systematic approach, especially if I don't understand the problem at all, what I'll do is that I'll just like the first step, understand the problem. To show that I understand it, I'll write it in my own words. The second step will actually to understand the input. What is it that they're giving me? And the output. What is it that I'm expected to give out, right? Then by doing that, that will actually help you to kind of like come up with your step 3, whereby you have to look at the edge cases. The edge cases are cases whereby, you know, like the input, like your array, what they giving you might be empty or might have one element. How do you then handle all of those edge cases, right? Then you move to step 4, whereby you're coming up with the brute force solution. It's not efficient, but one thing it can do, it can solve the problem, right? That helps you to kind of like understand the problem, like the core problem, right? Then you move to step 6, whereby you're kind of like trying to optimize it. And step 7, that's where you analyze the complexity. Okay, does this thing give me the runtime complexity which is expected, right? That's what I usually do, right? But in this case, what do we know that we're given? We know that we're given an array, right? They're saying that we're given an array, and this array is actually sorted in an ascending order, in an increasing order, right? So we can look at this binary search tree, and we can take 5 here because they're saying that anyway it's sorted in an increasing order. So we can take 5. What is another small number? It's 7. So the second largest, I meant to say, sorry about that. Then what is the third largest? It's 8, right? Then we're gonna take 9, just like that, right? 10. I'm sure you already have seen the pattern here, right? So we're gonna take 11. Then the last one is gonna be 13. So the pattern here essentially is an in order traversal, right? So why am I saying that? Because you can tell that we're starting from the left, then we go into the root, then we go into the right, right? So by using this technique, essentially all the time, we're going to get a sorted array, right? So you're starting from 5, you go into 7, you go into 8, 9, just like that. So it's like you go into the left, then you go into the root, then right, just like that, right? Cool. Now that we know this, then how can we then solve the problem? How can we then produce something similar to this, given this? right? So I think now I've kind of like cleared the confusion here, because we know that this is what they want, right? And we are given this. It's just that now we need to use this array to create this, what we just did now. Okay, so I know some of you might be, then let's go through the array like one by one, like, or sequentially, but that will be inefficient, right? The technique that I'm thinking of using, how about we use a binary search technique, right? Can use a binary search technique here. So a binary search technique, like I said, guys, the first video that I created, check it out, whereby we split the array into half, then we search on the half of the array, and just like that, iteratively, right? So in this case, what we want to do is that we want to get the mid, the center, like the mid, like, you know, here. Let me change my color so that you kind of like understand. So in this case, the mid, it's going to be 9, right? That's the mid number, right? So whenever we get the mid, you can tell, where was it lying? It was lying on the root, as you can tell. It was lying here. So what you want to do in the code, then you want to do something like this. When I say root equals to 9, right? Then, because we're using an in order, we have to go to the left subtree and we have to go to the right subtree. So we're not searching, we have to go through the entire array, right? So we're going to have to do something like this. We're going to say root dot left, right? Then you're going to give it your array, because you never want to give it the whole entire array. But when you give it the whole entire array, you don't want it to search the whole entire array. You want it to search on the left subtree, because you know all of these elements were coming from the left subtree. We're coming from here because they are small, okay? Then what you want to do is that you don't want to change your, binary search. You don't want to change your low index, which is 0, and your high index, let's just assume it was 7. I just made up that number. Then what you want to do is that you want to update your high, because that's where you want to start your search. So your high here will have to be here. So it's 0, 1, 2. So your high will be 2. So in this case, from code perspective, this will be a low, which is going to be 0. Then your high is going to be updated to 2. Where was it coming from? Initially, when we started, it was 7, right? Cool. Now let's go to the root dot right. Okay. So what about our root dot right? Our root dot right, we don't have to look here, because we know that all of these elements are representing the left subtree. We have to go to the right section, right? We also know this because of the root here. We know the principle of binary search tree. All the elements in the left subtree are going to be less than all the elements in the right subtree. We know that. So that's why here we are confident that, okay, after we have selected the center, which is 9, all of these elements are greater. That's it, right? All of these elements are greater. They are huge, right? So now what are we going to do in this? We're going to do the same thing. We're going to say array, right? For right subtree, we're going to say array. Then this is where the tricky part happens. We updated our low, but this time, what happened on the right? We don't want to update our high, right? Our high will remain the same, the high of the array, right? From code perspective, obviously, there's something we're going to do, but here, just for people to understand, high will remain the same. And what about your low? Your low will change. It will become the mid, right? The mid number, which is this. We can think of this, maybe it was 3 or something like that. Then we can take the mid plus 1. Then it's going to make us be here. So this is going to be our low, our new low. High does not change. Okay. So similarly, in this case, low was 0. High tier is going to be mid minus 1. So, right. That's what we're going to do, because it's going to bring us here, which is 2. Okay. Then I think those are the 3 main concepts that I wanted to bring. And there's something very important, right? This is something that I personally struggled with, whereby I think whenever you kind of like working with recursion, right? All the time, think of like there has to be a base case, and it has to come out like at some point, right? Like it's like writing a while loop. that does not end. Like, right? So every time whenever you think you're writing your recursion, think of how you're going to end it, like how it's going to end. I don't know if I'm making sense, guys. I'm sorry if I might be confusing, but like, it's like when you're writing your while loop, like while true, you know this will run forever, like it will run forever, right? You need to come up with an end case. So in this case, how would we then, because we know that we're gonna do this recursively, like, you know, going through this, like how would you then think of an ending statement? All of the problem that we have worked on, if it's a recursion, there has to be how we kind of like end something, right? Like that's how it is. So in this case, you can imagine that now we went up to here, like we went to the leaf or the last node, then you can keep on subtracting, you can keep on adding, like mid plus 1, you can keep on subtracting mid plus minus 1, like you will do that recursively, and you will see when we're writing code. So what comes to my mind is that to avoid this, our breakdown will be, then we're going to have to look at the low. So we're going to have to say, as long as if low is less than or equals to high, then we're just going to break. Like, that's it. Just return none or something, right? Just return none. Then we know that we have reached this statement. Because we're going to minus, you can imagine that we're going to subtract the high. Yeah, like we're going to keep on subtracting it because we're going to update it through the mid. Then we're going to get here. When we get to the base, which is the 5, like the leaf, we're just saying, okay, just please maintain the low. As long as the low, it is less than or equals to high, then that's fine. But if it passes this, then just return none. That's it. Okay. I hope, guys, I was able to kind of like explain this. I'm sorry if I didn't explain this very well. Let's go to the code and see how. Okay, guys. Let's see how we can actually go about solving this, right? So we know that we said we're gonna use a kind of like a binary search technique. So let me just create that function, binary search. So we're taking in the array. And we're gonna have the low index, which is gonna be starting at 0. Then our high index, initially. When we're starting with our recursion, is going to be none. And the reason we're doing this is because you can imagine that we want to update our high index whenever we're going recursively through the left subtree and the right subtree, right? So what we're going to do is that we're going to say if high is none, then we just want to define the high. We just want to say high equals to length. You take the array, then you subtract by 1. Okay, so if you don't understand what I'm doing, I'll say like watch my binary search video, then you will actually understand how kind of like binary search work. Okay, so like I said on the whiteboard, that all the time always think of like the terminating condition. Like I said, in this case, we're just gonna say if low is greater than high, we want to terminate this, because like you know that like the high index can be greater than the low. Like that's not how it's done, right? Like that means like we're going outside of the array, right? So that is going to be our terminating function. But in short terms, let me show you this tree. So you can see that minus 10 there, that is the smallest number. So like that is like the last value. So after then, just return none. If we go outside that just return none. So we're terminating the recursion. Cool. I think now we can just go ahead and create our mid value. Low plus high. So we're getting the mid index. Then we're gonna see mid number. The 9 that I just showed you is like now we're getting it because we're just gonna say array and we're indexing it by the mid number. Mid index, I mean to say. Right, then we're just gonna create the root because they said return a hide balance binary search tree. So they're expecting you to return the tree. So to return the tree, we're gonna use this class here that they define for us, which they call it tree node. So we're just gonna use that, and we're gonna pass in the mid number inside there. Okay, then we're gonna say root dot left. So now it's time for us to traverse, right? Like recurse, right? So to recurse, we just need to call our function binary search, right? And we're gonna give it the array, and we're gonna, because now we go into the left subtree, we don't have to change the law. Like, we go into the left, is always less than high, the right subtree, I mean to say. So what we need to do is that the only thing that we need to do is to update the high index. So it's gonna be mid -1. Then we're gonna have root dot right. Okay, then we're gonna have binary search tree. Oh, sorry. So I just needed to copy this. Sometimes I can be lazy to type. So okay, I'm just gonna say binary search tree, also pass it the array. So now, because we go into the right subtree, what you need to do is that we need to update our low, right? That means it's gonna be mid +1, then our height will then remain the same. Okay, and we're gonna return root because they're expecting a tree. Then we're gonna say return the function that we just defined now, which is binary search, and then it's gonna take the nums, which is the list that we've been given to us. So that's an array, so it's fine, we can just pass it here, and let's see what will happen. Okay guys, this worked, so this is cool, right? So now let's go to the second problem, which is similar to this, and let's see how we can actually solve it. Okay guys, if we can look at this problem, the second problem, which is balance a binary search tree, actually it's quite similar to the first problem. It's just that the first problem they gave us array. In this case, they're giving us actually the root, which is a binary search tree. So this time they're giving us the tree instead of an array. So how can we then take a tree, then return a balanced binary search tree? So they're still the same, because we have to return a balanced binary search tree, just like we did in the first problem, right? I can actually copy and paste that code. So I've copied that code, the first one that we wrote. Let me paste it here, because it's still relevant in this problem, because we know that they want us to return a balanced binary search tree. So this code that we just wrote, it will definitely work, right? The only problem is that this code, it expects array, and in this case they give us the binary search tree, right? That means we need to actually take this binary search tree, convert it into an array. Okay, so how can we go about this? So we're gonna say def, I'm gonna call this get array, doesn't matter. So then we're gonna take the root that they gave us, right? Like I said, every time you request, you need to think of like a terminating condition, right? So in this case, a terminating, because we're going to reach the leaf, then we're going to say if root, right, is none, then we want to return an array. Remember that we want the array. That's the goal. But now the question say the problem is how are we gonna get the array like in the tree, right? So we can now go to the left, like we get the key, we go to the we get the key of that, then we go to the left, to the right, we get the key of that, just like that, right? So that's how we can get, like, then we just add all of these inside an array. So something like this. So you can just say return, right? We can just say get array, okay, get array. So inside here, I'm just gonna say root dot left, right? Then I'm just gonna add it with then we're just gonna get the root dot val, like this value here. So there is like, that's how we're like gonna go about this. So you're gonna go to the left, then go to the right, then it's gonna be balance, then it's gonna say get array. So all of these, whenever they reach the terminating condition, the terminating condition will return array. So you don't return none, then that's when we add this array plus this, then definitely gonna work, right? Then we're just gonna say array right? Then now we're gonna say what's this, root dot right, right? Two functions. We have reused the first one, so now the only thing that is left, just gonna validate. I think we're fine. So let me just, yeah, I think we're fine. So let me just call these two functions. The first one is gonna be array, because we just want to say get array given the root, right? And then the second one, which is the binary search, so it's gonna return the root. Let me just say, I don't want to call it, I'm just gonna say binary search. Then I'm just gonna say take the array, because it wants the array, but I'm gonna say return that, right? I think let's look at the results. So we just used two functions. The first one was to get us the array, and the second one we reused the first functions that we explained, and then we used those two functions and the solution worked, right? Like, this is impressive. So yeah, guys, this is how like you kind of like use an easy problem to solve a harder problem. I hope you guys learned a lot. See you in the next video. Bye.